Hello friends, welcome to today's machine learning class, and in this class we will see the backpropagation algorithm for multi-layer neural network that will come under artificial neural network from first unit. Okay. First let us see one example for this multi-layer neural network, that is speech recognition system. Okay, in this system we are having a word that starts from H and ends from D. Okay. From this word we have to place vowels. So by inserting vowels in between H and D, we need to produce 10 different words. 10 different words like hide, had, heed, hood, etc. Okay. So what are the vowels we are having? A, E, I, O, U. So we have to place any of these words in between H and D so that we can create a new word. So likewise we have to create 10 different words. Okay, here the input speech signal is represented by two numerical parameters, that is see F1 and F2. These two are input numerical parameters from spectral analysis of sounds, okay, which allows us to visualize the decision surface over two-dimensional instance spaces. See, the x-axis is F1 and y-axis is F2. Okay, this F1 and F2, and this is the hypothesis space. And this is the hypothesis space. So based on the input value, we have to classify that particular word into any of these 10 words. Any of the 10 words. First one is head. See, head is here. Head. And second one is hid. See, H is HAD. Hid is here. Okay. And next one is HOD. HOD. Where is HOD? Plus symbol. See, HOD is here. Somewhat here. Okay. Likewise, the last one is HOOD. HOOD is here. Okay. Likewise, we need to classify all the input values with respect to the vowels which are inserted into that word so that we can get 10 output classes, right? So here the decision region is multi-layer feed forward network. Okay, the values will be given to the input layer initially, and all the values will be feed forwarded towards the output node. Okay, so this is called as feed forward network. Here the network inputs are F1 and F2. Okay, F1 and F2 are inputs obtained from spectral analysis of the sound, and 10 outputs are there. See, 10 different outputs are there. That is 10 possible vowel sounds which inserted between H and D. Right. Okay. The network prediction is the output whose value is highest. Right. Okay. The graph illustrate here. This is the graph, and this is the graph. The highly non-linear decision surface represented by the learned network. So there is no linear classification here. This graph produces no linear classification. The classification is very high because this is non-linear decision surfaces are there, and the points shown in the plots are test examples distinct from the examples used to train the network. So we have taken a fixed training set to classify the data, right? And now let us see the working of multi-layer neural network. Okay, here we are having n number of input, that is x1, x2, etc. up to xn. These are all input to this network. Input to the network, and for all the input we are having the corresponding weight w1, w2, etc. up to wn are the weights which are assigned to the corresponding input values. Okay, normally weight is a minimum value or a small value will be assigned to all the weight, and x0 is nothing but the bias. Okay, here it is assigned to 1. Okay, and all these values will be given to the summer unit. Okay, so the output of summer unit is net is equal to I equal to 1 to n, that is summation of I equal to 1 to n wi into xi, right. Okay, and this net is given to the sigmoid unit, which is otherwise called as threshold unit. That is, the output of threshold unit is sigma net. Okay, sigma net, which is equal to 1 by 1 plus e power minus net, which is called as sigmoid. That is sigma of y, which is equal to 1 by 1 plus e power minus y. The sigmoid unit first computes a linear combination of its input. Okay, that is, it add all the inputs and the weight, that is summation of I equal to 1 to n xi wi. Okay, after that this value will be given to the threshold unit. Okay, here the threshold output is a continuous function of its input. This is important. Okay, the sigmoid unit computes the output O as sigma of w vector multiplied by x vector. Okay, we know the sigma of y, which is equal to 1 by 1 plus e power minus y. Therefore 1 by 1 plus e power minus w vector into x vector. Here the sigma, that is the sigmoid function, which is otherwise called as the logistic function, its output range between 0 and 1. Okay, so that we are using this particular symbol. So this is 0, this is 1. The output, this is 1, sorry. The output of sigmoid function that lies between 0 to 1 only. Here the sigmoid function maps the very large input domain to a very small output. Okay, which is otherwise called as squashing function. Okay, this is called as squashing function, and it has useful property that derivates easily expressed in terms of its output. Okay, that is differentiation of sigma of y divided by differentiation of y, which is equal to sigma of y into 1 minus sigma y. 1 minus sigma y. Here e power minus 1 in the sigmoid function is replaced by e power minus k into y. Here the k is some positive constant value that is used to determine the steepness of the threshold. Backpropagation algorithm for multi-layered neural network. So in this network we are having n number of inputs. See x1, x2, etc. up to xn. So n number of inputs to this network. So the input layer consists of n number of nodes, input nodes, and for all the inputs we have to assign the weight for the corresponding inputs, w1, w2, etc. up to wn. So the weight value will be multiplied to the input, and that will be the output of this particular one, o1, o2, o3. Okay, on, sorry. So the multiplication of input with the weight will be the output of this particular function, isn't it, input layer function. And in this network we are having two hidden layers. This is hidden layer 1 and this is hidden layer 2, and finally we are having output layer. Here we are having m number of outputs. See y1, y2, etc. up to ym. Hence m number of outputs are there in this network. Okay, in this network which contains y number of output units rather than a single output unit. Hence we need to compute the error. So how do we define this error? E of w vector, which is equal to 1 by 2 summation of d belongs to capital D. Capital D is a training set. Hence D indicates the number of input units. So how many input units we are having? D equal to 1 to n multiplied by K belongs to outputs. Okay, K belongs to outputs. How many outputs we are having? Y number of outputs we are having. So K equal to 1 to m of TKD minus OKD whole square. Here TKD is the target output and OKD is the computed output. Okay, here the output is the set of output units in the network, that is Y number of outputs are there, and TKD and OKD are target output and the computed output values, which are associated with the kth output unit of the training example D. Okay, for example, we can take this particular training set. For this particular training set, what will be the output y1 to yn? In multilayer neural network, that is, if the network has more number of output units, then the error surface can have more number of multiple local minima. Okay, this is a very big drawback in gradient descent algorithm because it guarantees only to converge towards some local minimum instead of the global minimum. Okay, to overcome this, we can use the backpropagation algorithm. This is an excellent algorithm which results very good results in many real world applications. And this is the backpropagation algorithm. For this algorithm, we are having 5 inputs. See, training examples, learning rate, number of input layer nodes, and number of output layer nodes, and number of hidden layer nodes. So these are the different inputs, that is 5 inputs given to the backpropagation algorithm. See, when come to training samples, it containing a pair of input comma target output. Okay, x vector is nothing but the input to the network and t vector is nothing but the target of the network output values, and n is nothing but the learning rate, normally a very minimum value, this is 0.05 in our case. Okay, and n in is number of input nodes, number of inputs to the network, and n hidden is number of units in the hidden layer, number of units in the hidden layer, and n out is the number of output units, total number of output units is n out. Okay, here the input from unit I to unit j is denoted by xji. Okay, that means if x will be travelled from 1 to 2 means this is x12, and the corresponding weight is nothing but wji. For xji we have to add one weight, isn't it? So this is otherwise called as w12, that is the weight is assigned between the nodes 1 and 2. Okay, now we have to create a feed forward network with n input units, n hidden units, and n output units. Okay, see, we have to give the input to this network, and these input values will be travelled towards the output unit along with its weight, isn't it? So this is called as feed forward. The input values will be feed forwarded to the network. And the next one is initialize all the network weights to the small random numbers. Okay, so we have to initialize the weight values for all the input values, that will be between minus 0.05 to plus 0.05. The weight value should be between minus 0.05 to plus 0.05. And the third step is, until the termination condition is met, we have to do the following step repeatedly. Okay, the first one is, for each training sample x comma t, Okay, X is the input value, T is the target output value. That is training sample. We have to do the following things repeatedly. What are the things? Propagate the input forward through the network. Propagate the input forward through the network. Okay, so the input values will be given to the network and that will be propagated throughout the network. The first step, input the instance X to the network and compute the output for this node for every unit. So for every unit we have to compute the output. We have to give the input X and the output will be T. Okay, for all the units. And the next one is we have to compute the errors, that is propagate the errors backward through the network. This is the first step, input forward through the network and propagate the error backward through the network, because if this is the output here, if there is error in this particular output, what we have to do, we have to adjust the weight of all the hidden layers which are connected to the output layer, isn't it? So if there is any error here, we need to adjust the weight. Simultaneously we have to adjust all the weights in the nodes through the entire network. So this is, the error will be propagated backward through the network. Okay, so for each network output unit, calculate the error term, that is delta K. Okay, here we are having K number of output units there. Delta K, which is equal to OK, that is the calculated output. OK means calculated output, and Tk means target output. Okay, delta K, which is equal to OK into 1 minus OK into Tk minus OK, and this is the calculated error term of output unit. And simultaneously we have to calculate the error term of hidden units also. So here we are having H number of hidden units, hence the delta H, which is equal to OH into 1 minus OH into summation of K belongs to outputs. K belongs to outputs because we are having more number of hidden units, isn't it? So for all the hidden units we need to compute the summation of WKH into delta K. Okay, so the output will be summed of all the hidden layer units. Okay, then update each network weight. Update each network weight. So WJI is old weight. Old weight will be updated with the, sorry, this one is the new weight and this one is the old weight, and this is the delta Wi, which is computed from the network, right, where Wij, which is equal to learning rate, and this is the delta J, that is the error rate, and this is the input of the corresponding node unit. Okay, so by using this formula we need to adjust the weight of the entire network, and this process will be repeated until we get Tk, which is equal to OK, that is target output is equal to computed output. The delta R value for the unit R in the layer M, that is for every layer we are having n number of nodes are there. Okay, n number of nodes will be there in all the units. Okay, for example, let us take this particular unit. This is unit R in layer M. This is layer M plus 1. Okay, right. So we have to compute delta R, which is equal to OR. OR is nothing but the output, computed output. Computed output into 1 minus OR multiplied by summation of S belongs to layer plus 1. see in this layer m plus 1 into WSR into delta S. Okay, now calculating delta for any internal unit, okay. So any internal unit which is equal to delta R, the same formula, the delta R which is equal to OR into 1 minus OR into multiplied by summation of S belongs to downstream of R WSR into delta S. Okay, here downstream is nothing but the set of units immediately downstream from the unit R in the network. Okay, here all the units whose inputs includes the output of unit R. See, for every unit we have the input as well as output. Okay, now next let us see the derivation of backpropagation rules. So before deriving the backpropagation, now let us see the important notations which are used for this derivation. The first one is xji, that is the ith input to the unit j. Okay, for this unit, this is unit j, ith input xi. Xi is given to jth units, hence this is called as xji. And next one is wji, that is weight associated with ith input to unit j, the corresponding weight wji. And the next one is net j, which is nothing but the weighted sum of input for the units. Okay, the sum of all weights for this particular unit, that is summation of I wji into xji. Okay, next one is oj, that is the computed output by the unit j, and tj is nothing but the target output of unit j. And next one is sigma, this is sigmoid function of this unit. And output s, outputs. Okay, output is nothing but the set of units in the final layer of the network. Final layer is obviously the output layer. So number of outputs are equal to number of nodes in the output layer. And next one is downstream of j, which is equal to a set of units whose immediate input includes the output of unit j. Here for each training example D, we need to update the weight of Wij. Okay, how do we update this weight? By adding this delta Wj. So computing delta Wj is minus learning factor into dEd by dWji. Ed is nothing but the error factor, error of this corresponding weight. Okay, here Ed is error on the training example D and summed over all the output units in the network. Okay, here Ed with respect to W, which is equal to half of k belongs to output, that is sum of k belongs to outputs, Tk minus Ok whole square. Tk is target output, Ok is computed output. Computed output. Okay, here output is set of output units in the network and Tk is target value of unit k and Ok is output of unit k given in the training example D. And now let us see the two different training rules. The case 1 is training rule for output unit weights, and in case 2 we will see the training rule for hidden layer units. Okay, first let us compute this Wji, that is weight of ith weight in the jth unit, can influence the rest of the network only through net j, that we know very well, and this net can influence the network only through oj. Hence we have to apply the chain rule with the value oj. Okay, so the equation will be, this equation will be rewritten by including the chain rule doj here and doj here. The same equation will be rewritten by applying the chain rule. and we know already the ED, which is equal to 1 by 2 summation of k belongs to outputs of Tk minus Ok whole square. Okay, in the previous slide we have seen. Hence, the differentiation of ED divided by differentiation of OJ, which is equal to differentiation of 1 by 2 summation of k belongs to outputs of Tk minus Ok whole square divided by dOJ. Okay, and here the differentiation of Tk minus Ok whole square divided by Oj, which is equal to 0 if this is not, that is j is not equal to k. If j is equal to k, then it will get some values. Okay, if j and k are different, then only the value will be 0. Okay, so here differentiation of ED divided by differentiation of OJ. Let us take this particular one. Only this thing. We can take the first part of equation, which is equal to differentiation of 1 by 2 Tj minus Oj whole square divided by differentiation of Oj. And now let us take this half uh, to the beginning of this equation, hence 2 will be cancelled, that is differentiation of these two things, which is equal to 2 into Tj minus Oj into differentiation of Tj minus Oj divided by differentiation of Oj. Hence we can remove these two, and here Tj minus Oj, this is 0, this is minus 1. If we differentiate Tj, then it will get 0. If we differentiate Oj, this will give 1. Okay, this is also 1. Hence the result is minus Tj minus Oj. Okay, minus into minus, here plus is there, minus is there, and minus into plus is minus, so minus Tj minus Oj. Since Oj, which is equal to sigmoid of net j. Okay, and the sigmoid of differentiation of Oj divided by differentiation of net j, which is equal to sigmoid of net j into 1 minus sigmoid of net j, isn't it? Hence this particular equation, which is equal to differentiation of sigmoid of net j divided by differentiation of net j, which is equal to Oj into 1 minus Oj, Oj into 1 minus Oj, and therefore this particular equation, which is equal to this one. And now we are going to combining the delta Wij, which is equal to minus learning rate differentiation of Ed divided by differentiation of Wij, and the differentiation of Ed divided by differentiation of Wij, which is equal to differentiation of Ed divided by differentiation of net j into Xij, which we have seen in the previous slide, isn't it? So we are going to compare these two equations, then we will get sigma delta Wij, which is equal to this one, and which is equal to learning rate into Tj minus Oj into Oj of 1 minus Oj into Xj. Okay, this is taken from this particular equation. Okay, and this one, we are going to combining these two equations, this one and this one. And the case 2 is the training rule for hidden unit weights. Okay, here J is internal unit or hidden unit in the network, and Wji is the weight of jth input to the ith unit, right, and which can be influence the network output as well as the network error, and set of units are called as downstream of J. And here net J can influence the network output. Net j is with respect to the net j only the network output will be produced, and this is called as ED, that is error of dth unit, okay, only through the units in the downstream j. First let us take this particular equation, that is differentiation of ED divided by differentiation of net j. Here we have to include this net k as a chain rule, that is differentiation of net k in the chain rule. Hence we have to rewrite the same equation, summation of k belongs to downstream of j, which is equal to differentiation of ED divided by differentiation of net k multiplied by differentiation of net k divided by differentiation of net j, okay, and here this particular term will be rewritten as minus sigma k, okay, just we have seen in the previous slide. Hence we can rewrite the same equation into summation of k belongs to downstream of j minus sigma k into differentiation of net k divided by differentiation of net j, okay. Now we have to include the output differentiation of output in the equation by applying the chain rule. So we have to rewrite the equation like this form, and here we know this particular term is nothing but wkj, okay. Now we have to rewrite the equation in this form. So by substituting wkj in the place of differentiation of net k divided by differentiation of oj, okay. After that, see this particular term, differentiation of oj divided by differentiation of net j, which is equal to oj into 1 minus oj, okay. Hence we have to rewrite the entire equation is in this form, and after that rearranging the term using the delta j to denote this particular form, that is this equation, okay. Differentiation of d divided by differentiation of net j, we have, see this one, which is equal to oj into 1 minus oj into summation of k belongs to downstream of j delta k into wkj, okay, and the delta wji, which is equal to learning rate into delta j into xij, right. Up to this we have seen the backpropagation algorithm for multi-layer neural network from the artificial neural network, and you can expect this question from 5-mark question of your university examination, okay. For more information please go through your textbook. Thank you.